We see a lot of moving objects in our daily life. But what if we could take a closer look at the motion of objects? Physics provides a valuable tool for studying motion, which is known as kinematics. Today in this video, we'll take a closer look at this area in physics and analyze motion in one dimension. When an object's position changes with respect to time, we say it to be in motion, just like a moving car. Its position changes continuously with respect to time unless you stop it. Now suppose you drive the car from a point A to a point B. You must have covered a certain path from A to B. It could be a straight line, a curved path, or even an irregular shape. The length of this path is known as the distance. And now, the length of the shortest path joining these two points is called displacement. Distance and displacement are the same ideas, but with a bit of difference between them. Distance is a scalar quantity. It tells you the length of the path you covered. And displacement, on the other hand, is a vector quantity. It tells you how much path you have covered effectively in a straight line and in which direction relative to your starting point. Now imagine you made that journey from point A to point B. You didn't just magically teleport, did you? It took you some time to cover that distance or achieve that displacement. Think about it this way. If you covered a large displacement in a short amount of time, you were moving quickly. This quickness of your change in position is what we call velocity. Just like displacement, velocity is also a bit picky about direction. It tells you not just how fast you are moving, but also in which direction you are moving. So, if you are driving north at 60 kilometers per hour, that's your velocity. If you just say you're going 60 kilometers per hour, that's your speed, the rate at which you are covering distance. And just like distance, speed doesn't care about direction. It's a scalar quantity. Now let's say you're driving and you want to go faster, or maybe you need to slow down because of traffic. To change your velocity, either its speed or its direction or both, you need to accelerate. Acceleration is basically the rate at which your velocity is changing. If your velocity is increasing, you are accelerating in the direction of your motion. If your velocity is decreasing or you are slowing down, you are also accelerating but in the opposite direction to your motion. We sometimes call this deceleration or negative acceleration. Just like velocity and displacement, acceleration also has a direction, making it a vector quantity. It tells you how quickly your quickness is changing and in what direction that change is happening. Okay, so we have been talking about these ideas of distance, displacement, velocity, and acceleration in a descriptive way. But in physics, we like to be precise, and that often means using math. So let's put some mathematical definitions to these terms, especially as they relate to motion in one dimension. Let's say an object is moving along our one-dimensional line. We call it the x-axis for simplicity. Displacement. If an object starts at a position xi at a time ti and ends up at a position xf at a time tf, then the displacement is mathematically defined as the change in its position delta x equals to xf minus xi. Remember, this is a vector quantity, so the sign of delta x tells us the direction of the displacement. A positive delta x means displacement in the positive x direction, and a negative delta x means displacement in the negative x direction. Average velocity. The average velocity is defined as the total displacement divided by the total interval over which that displacement occurs. V equals to delta x by delta t. Again, velocity is a vector, so its sign indicates the direction of the average velocity. Instantaneous velocity. while the average velocity tells us the overall rate of change of position over a time interval, instantaneous velocity tells us how fast and in what direction an object is moving at a specific instant in time. Mathematically, we can think of it as the limit of the average velocity. As the time interval delta t becomes infinitesimally small, v equals to limit delta t tends to 0 delta x by delta t, and which is equals to dx by dt. For those familiar with calculus, this is the first derivative of the position with respect to time. For those who aren't, just think of it as the velocity at a single precise moment. Average acceleration. Just like average velocity relates to the change in displacement over change in time, average acceleration relates to the change in velocity over time. If an object has an initial velocity vi at time ti and final velocity vf at time tf, then the average acceleration vavg is equals to delta v by delta t. Acceleration is also a vector, and its sign tells us the direction of the average acceleration. Instantaneous acceleration. Similar to the instantaneous velocity, instantaneous acceleration tells us the acceleration of an object at a specific instant in time. It's the limit of the average acceleration as the time interval delta t approaches 0. It is also the second derivative of position with respect to time and the first derivative of velocity with respect to time. Again, for those who don't know calculus, just think of it as the acceleration at a single precise moment. And just to reiterate, distance and speed don't have a direction associated with them. In this basic mathematical framework, distance is simply the total length traveled and average speed is the total distance traveled divided by total time. Instantaneous speed is the magnitude of the instantaneous velocity. So these are the mathematical ways we define these fundamental concepts in one-dimensional motion. They give us the tools to be much more precise in our analysis and to start deriving those important equations we'll talk about later. Alright, so we have talked about what motion is and the basic ingredients like distance, displacement, velocity, and acceleration. Now, let's think about the different flavors or types of motion you might encounter, especially when we are sticking to our straight line, one dimensional world. The simplest kind of motion you can have is when your velocity stays exactly the same. Imagine you're driving on a perfectly straight highway with your cruise control locked in. You're not speeding up, you're not slowing down, and you're definitely not changing direction since we are only going in one dimension. This kind of motion where your velocity remains constant is called uniform motion. Since your velocity isn't changing, that also means your acceleration is zero in uniform motion. It's like cruising along a steady pace. But let's be real, most of the time things aren't that simple. You might speed up to overtake someone, or you might brake when you see a red light. In these situations, your velocity is changing over time. This kind of motion, where your velocity is not constant, is called non-uniform motion. Now, within this non-uniform category, there is a special and very important type. Imagine you're pressing the accelerator of your car down by the same amount consistently. Your speed is increasing and it's increasing at a steady rate. This means your velocity is changing, but it's changing in a uniform way. This is called uniformly accelerated motion. In this type of motion, the acceleration itself is constant. It's a step up from just having a constant velocity. Now, the rate of change of that velocity is constant. This is the kind of motion we'll spend a lot of time looking at because it follows some nice and predictable rules, which we will get to later with the equation of motion. So, to recap, in our one dimensional world, we can mainly talk about uniform motion, non uniform motion, and uniformly accelerated motion. Alright, let's dive into one of the most useful tools we have for analyzing uniformly accelerated motion. The equations of motion. These are a set of mathematical formulas that relate displacement, initial velocity, final velocity, acceleration, and time when the acceleration is constant along a straight line. Think of these equations as shortcuts instead of having to analyze the motion from scratch every time. If we know some of these quantities, we can use these equations to find the others. There are typically three main equations of motion we focus on in basic kinematics. The first equation of motion, relating final velocity to initial velocity, acceleration, and time. Imagine you start with an initial velocity. Let's call it u. Then you experience a constant acceleration, let's call it a, for a certain amount of time t. What will your final velocity v be after that time? Well, we know that acceleration is the rate of change of velocity. Mathematically, we defined average velocity as a equals to delta v by t. If we rearrange this equation to solve for the final velocity, we get our first equation of motion v equals to u plus at. This equation tells that your final velocity is equal to your initial velocity plus the product of your constant acceleration and the time for which you accelerated. Simple, right? The second equation of motion, relating displacement to initial velocity, time, and acceleration. Now, let's think about the displacement s. During this uniformly accelerated motion, we know that the displacement is related to velocity and time. If the velocity were constant, we'd simply have s equals to v times t. But here, the velocity is changing. However, for uniformly accelerated motion, the average velocity over time interval t is simply average of the initial velocity u and the final velocity v. Average velocity equals to u plus v by 2. Since displacement is average velocity multiplied by time, we get s equals to u plus v by 2 times t. Now, if we substitute the first equation of motion into this equation, we get our second equation of motion, s equals to ut plus half at squared. This equation tells us the displacement of the objects in terms of initial velocity, the time for which it moved, and its constant acceleration. The third equation of motion, relating the final velocity to initial velocity, acceleration, and displacement. Sometimes we might not know the time for which the motion occurred, but we might know the displacement. In that case, we can use our third equation of motion, which relates the final velocity v to the initial velocity u, the constant acceleration a, and the displacement s. We can derive this by taking our first equation v equals to u plus at and solving for time. T equals to delta v by a. Then we can substitute this equation for t into our equation for displacement using average velocity. S equals to u plus v by 2 times t. S equals to u plus v by 2 times u minus v by a. S equals to v square minus u square by 2a, and rearranging this equation to solve for v square, we get our third equation of motion, v square equals to u square plus 2s. This equation is particularly useful when time is not given for or not required in the problem. In summary, the three equations of motion Or for uniformly accelerated motion in one dimension r, v equals to u plus at, s equals to ut plus half at squared, v squared equals to u squared plus 2as. Alright, so we just talked about the equations of motion which are super handy for constant acceleration. Well, guess what? There is a really common situation where the acceleration is constant. When the things are falling, we call this free fall. Basically, if you drop something and we ignored air being annoying and pushing back, the only thing really pulling on it is gravity. And near the earth, that pull causes a pretty steady acceleration downwards. We give that acceleration a special name, g. It's written as g. And it's about 9.8 meters per second squared, or roughly 10 if we are feeling lazy with numbers. So, free fall is just like our uniformly accelerated motion, but acceleration is always downward. So, free fall is just like our uniformly accelerated motion, but the acceleration is always downwards and equal to g. Now, when we use our regular equations of motion for free fall, the a just becomes g. We also often talk about the up and down direction. So instead of s for displacement, you might see y being used for the vertical distance. So our equations look pretty much the same, just with a g instead of an a. How fast you are going after some time. V equals to u plus gt. How far you have fallen or risen after some time. Y equals to ut plus half gt squared. And how fast you are going after falling a certain distance. V square equals to u square plus 2gy. The same sign rules apply here too. So the big takeaway is that free fall isn't just some magical new type of motion. It's just a regular constant acceleration motion where that constant acceleration is due to gravity. Just be mindful of which way you are calling positive and make sure your signs for g and your initial velocities and displacement match that choice. Alright folks, that brings us to the end of our journey into understanding motion in one dimension. We have covered the basics, what motion is, the key terms like distance, displacement, velocity and acceleration, the different types of motion you can encounter, the powerful equations that govern uniformly accelerated motion, and even a special case with free fall. Hopefully this video has helped you wrap your head around these fundamental concepts of kinematics. Remember, understanding motion is a crucial stepping stone in physics, and these ideas will pop up again and again and again as you delve deeper into the subject. If you found this explanation helpful, don't forget to hit that like button. It really helps the channel grow. And if you have any questions or suggestions for future topics, please leave them in the comments below. I always love hearing from you. If you want to continue your physics adventure with DeltaMind, make sure to subscribe so you don't miss out the future topics. We'll be tackling more exciting topics soon. Thanks for watching and keep exploring the world around you. Until next time, this is DeltaMind signing off. Keep thinking.